So here is question number 6, in which we can see that a ball is thrown onto a floor as shown in figure. If the velocity vector v1 is 3i minus 4j cap and the coefficient of restitution is 1 by 2, then the velocity v2 by which it rebounds will be what? We have to calculate this velocity v2, the velocity after it rebounding. As we can say that x component of velocity is not changing, only y component will change here. Now let us break in the components. v1 has one component in x direction, v1x, v1x, y component in negative y direction, that is v1y. Similarly, break v2 into their components. One will be toward x, that is v2x, other will be toward positive y, that is v2y. Now we can say that the ball is approaching the surface with v1y speed. The ball is separating by the surface with v2y speed, and we know the very famous relation in the collision that velocity of separation is always equals E times velocity of approach, where E is known as coefficient of restitution, that is given in your question. So velocity of separation, we can write v2y equals coefficient of restitution given 1 by 2 multiplied by velocity of approach is v1y, that is 4 given in the question. So 1 by 2 multiplied by 4 equals 2 meter per second. Now we have got the x component of v2, which is not changing, which will be same as v1x. We have got the y component of v2. Now we can have v2 in vector form, that is 3i cap plus of twice j cap. Now if we see the options, we will find that option number 2 is matching perfectly. So we will go with option number 2. Now let us proceed to the next question, that is question number 7. A solid cylinder of length L is in equilibrium in two different liquid A and B as shown in figure. The density of liquid is 3 rho by 2 and the density of liquid B is 3 rho. Find out the density of cylinder. Now if you see, we can find that a cylinder is in equilibrium condition and immersed in the liquid. So since cylinder is in equilibrium condition, therefore F net on it will be 0. We can say that weight of the cylinder is equal to net upthrust force by the liquid. Weight of the cylinder we can write mass of the cylinder into gravity, and mass of the cylinder equals volume into density. Suppose the density of cylinder is small d. Volume of cylinder is given by area into length. So AL becomes volume of cylinder, D becomes density of cylinder. Volume into density becomes mass multiplied by gravity. Now we have got the full expression for weight equals net upthrust force by the liquid. Here two liquids are there. So upthrust force by the liquid A will be given by volume of object inside the liquid, that is area of object multiplied by length of column of cylinder in liquid A is 2L by 3 multiplied by density of liquid A, that is 3 rho by 2 multiplied by gravity, plus of upthrust force by the liquid B is volume of cylinder inside the liquid B is A times L by 3 multiplied by density of liquid B is 3 times rho multiplied by acceleration due to gravity G. Now let us take the terms which are cancelling, G, G and G. Area, area and area. Length, length, length. So we will get the value of d in terms of rho only. After solving, we get density of the solid cylinder will be given by 2 times rho. So if you see the option, we'll find that option number 4 is absolutely correct. Now let us proceed to question number 8. An ideal gas undergoes a process P to Q and ultimately Q to R as shown in pressure volume diagram. The work done by the gas will be what? Now we know that work done by the gas is always equals area under PV diagram. Therefore, now let us calculate the area under PV curve, which will be given by, consider this as complete rectangle and this as triangle. The area of triangle gives A1, the area of rectangle gives A2. So the total work done W is given by A1 plus A2. Here, now how we will calculate the A1, that is area of rectangle? The base is 2V naught long. The length is 4 times P naught. So the area equals length into breadth. That's why 8 times P naught V naught. Plus area of triangle, half of base. This base is V naught into height. This height is 2P naught. So after solving, we will get the work done by gas equals 9 times P naught V naught. And if we see the option, we'll find that option number 3 is absolutely correct. So we go with option number 3. Now let us proceed to the question number 9. The displacement time xt graph of a particle executing simple harmonic motion SHM is shown in the figure. The equation of SHM will be what? Now we have to calculate the equation of SHM. Now we know that a general equation of SHM is given by x equals a times sine of omega t plus delta, where delta is the initial phase, a is amplitude, omega is angular frequency. After observing the curve, we can say that amplitude is 4 centimeter. We can say that the time period, we can guess from the graph, that is half of cycle, that is pure negative cycle, is covered in 1 second. It means the total time period is 2 seconds. As a result, omega 2 pi by capital T comes pi. Putting the value of amplitude and omega in our equation of displacement, we will get x equals 4 times sine pi t plus delta. Now our next target is to calculate the delta, which is initial phase or phase at t equal to 0. So at t equals 0, what is our displacement of the particle at t equals 0? At t equals 0, the particle is displaced from the mean position by 2 centimeter. So x equals 2 centimeter. Putting this 2 in the equation, we get 2 equals 4 times sine of pi t. This term will be reduced to 0. You will get only delta. From here, you will get sine delta as 1 by 2. So delta will be. Now you have to calculate delta very much carefully. This is because, see, this is, let us consider the particle was moving along this line. It was executing SHM along this line. So this is mean position. The motion can be understood in 4 quadrant or 4 parts. Going away from mean to extreme in one direction, this is part 1. Returning back toward mean position, this is part 2 or quadrant 2. Now going again extreme position in other direction or in opposite direction, this is part 3, and finally returning to the mean position, this is part 4. Now analyze the situation given here. The particle is returning toward the mean position from extreme position. So if we are taking it positive and negative, so particle is returning from positive toward mean position, so it is lies in second quadrant. So angle we may get pi by 6 as well as 5 pi by 6 and so on. So pi by 6 lies in the first quadrant, 5 pi by 6 lies in the second quadrant, and this will suit because particle is returning toward mean position from positive direction. And the final equation will be given by x equals 4 times sine of in bracket pi t plus 5 pi by 6. This is the final answer. Option number 4 is absolutely correct. Now let us proceed to the next question, that is question number 10. Temperature and volume of 1 mole of an ideal monoatomic gas in process are related as Tv to the power 2 by 3, which is equals constant K, where K is a constant given in the question. The molar specific heat capacity for the process will be what? Means we have to calculate molar specific heat capacity, capital C. Now first of all, let us see the relations given in the question. Tv to the power 2 by 3 equals constant. Now let us convert it in Pv to the power something. Using ideal gas equation, T will be replaced by Pv divided by Nr. We just have used ideal gas equation. V to the power 2 by 3 equals constant K. Now after solving, we will get P times V to the power 5 by 3. Rest of the things, that is number of moles constant, R constant, will be hidden in another constant, capital K. This is the equation of polytropic process. This equation shows that the process is polytropic. And for a polytropic process, the molar specific heat capacity is given by specific heat capacity for constant volume plus R divided by 1 minus alpha, where alpha is a polytropic process is given by Pv to the power alpha K. So after comparing, you will get your alpha as 5 by 3 and monoatomic gas is given. So the Cv for a monoatomic gas you already have calculated 3R by 2. Now putting these values of alpha and Cv in C equation, we will get C as 3R by 2 plus of R minus 1 minus 5 by 3. Now after solving, you will get C equals 0. So the molar specific heat capacity here will be 0. Now let us proceed to the next question.